Okay, good evening, everyone, and welcome to this public talk on mysteries of the sun. And today we're joined by our speaker for the day, Dr. Vagish Mishra. Just a quick, how many of you have been to IIA before here? And how many are your first-time visitors to IIA? Oh, nice. So I'd like to welcome you to the Indian Institute of Astrophysics here in Koramangala. Just to give you a very quick introduction, we are an astrophysics research institute and we do research in all fields of astro. That includes solar, solar system, galaxies, extragalactic cosmology, and theoretical stuff as well. Okay, and we're also a DST funded institute. And let me quickly get to why we're here today. How many of you saw their social media bombarded with a lot of Northern Lights pictures earlier this month? Right? In fact, it was literally like this in every newspaper, every article, everything, right? And I'm pretty sure all of your social media explore would have looked like this, where all you would see are just aurorae pictures and all that, right? And if you can see, we're here to talk about why this particular thing happened and this thing. Right now, that's something very special for us, right? Because northern lights, by definition, are supposed to be in the north. But then our latitude, if you know, we're quite low in the northern hemisphere. So technically, we're not supposed to get it. But then we did. And so here we are today to learn about why this is happening. And joining with us, the speaker is Dr. Vagish Mishra. He is a faculty member here at the IIA and he works in the solar group. Right? He has a PhD in solar and heliospheric physics, which means he studies the sun in great detail. And before joining as a faculty here, he's done his postdoc at the Max Planck Institute in Germany. His primary research interests include coronal mass ejections, which is a specialty of today, which you can also see here, and we'll talk more about it later. And he also deals with space weather, right? So we deal with weather on Earth and weather in Bangalore, but he deals with space weather. Right? And apart from all of these academic things, he's also known for giving popular talks in English and Hindi to the general public. Right? And without further ado, I'd like to welcome Dr. Vagish to continue with this talk.
So, hello, am I audible?
Yes.
Okay, good. So, hello everyone and good evening. So, I will be talking about the mystery of the sun, and thanks to Vikrant for...
You have to share your screen on Zoom so that the people online can also see it. All right. And can we go full screen on this? Lovely.
Thank you, and thanks Vikrant for introducing me. So, I will be talking about the mystery of the sun in general, and later I will try to explain the aurora. And we know that sun has been like a fascinating object in heaven, space, for a long time. All mythology, if you see around the globe, be it Greek mythology, Indian mythology, they have considered sun as a central attraction in their all stories, myths, and everything. Because for a long time, people understood, even ancient to ancient civilization took help of the sun to understand time. And if you see here, crops, tree, everything is not possible on the earth without sun. So I basically work in the solar astrophysics, and the outline of my talk would be starting from the brief introduction, why sun is so special to us, and different atmosphere and other things. So the outline, what I will be going to talk is shown in this animation. You might see in the, just here the sun, and from the sun not only the light comes to us, but lot of particles and mass is coming from the sun, and when it reaches to the earth, like any other planets in the solar system, it actually can damage lot of things, space weather. This phenomena is called space weather, when something from the sun can come and disturb power grid on the earth or even the satellite in the space. It can affect all the GPS.
Changing slide.
Sorry for interruption. Yeah. Here I think it's paused. So yeah, resumes here. Yeah.
Can you quickly repeat a little bit?
Yeah. That's fine. So the brief outline of my talk is animated here. From the sun, huge expulsions of mass is coming, and then it is interacting with the Earth's magnetic field, and we can see here that it can in fact damage power grids on the Earth. It can damage satellites into space. So all the infrastructure in either space or ground can be affected by the sun, and this whole branch is called Sun-Earth connection, because in today's era, we are highly dependent on the space technology, be it satellite, GPS communication, or even television, anything. And that can be very badly affected. So I will show some examples where this phenomena has really impacted the space infrastructure in a very significant way. So to start with, this is a beautiful aurora what Vikrant was talking, and we can see that aurora is really beautiful. The people living in the northern hemisphere, especially at higher latitude, get this chance very frequently to see such aurorae. But in India, being at latitude very low, like even our Ladakh place where we have seen aurora this time is at 32-degree latitude. And if we compare Bangalore, it's 10-degree north. So we can see that this is very low latitude. We are in the low latitude. And from India, there are not enough historical records that aurora has been seen from Indian soil in the past. So this is very interesting and historical events which we will be going to talk about. And then just to connect, sun is not a very different thing than doing astro. So in the broader context, if we see, we can see that if in this plot, basically what I want to show that different stars have different temperature and different luminosity. But if we see, sun is somewhere here. So neither the sun has very high temperature, neither very high luminosity. So in that sense, our sun daytime star is an average star. But we study in great detail. In the night sky, we see several other stars. But most of these stars, if you see, 90% of them are similar, like in the main sequence where on the same line sun is there, and 75% of them are dwarfs. So at least we can say if we understand the sun in great detail, other tiny objects into space which we don't actually have very high resolution images or the observation we can understand. And this is the approach solar physicists take. They try to understand sun in great detail and extrapolate this knowledge to understand other far objects, and then try to understand the bigger universe. But the catch is, if we just compare the light coming from the sun brightness, it has some variation over years also. But other, if you take very similar stars similar to sun, when I say similar to sun, having similar mass, similar radius, probably similar luminosity, from the space people have observed fluctuations, lot of fluctuations. It means in that sense our sun is not that much having variability. So again, when we extrapolate the information from the sun to other stars, it's not so simple, and there we need to use lot of models and calculations. But sun provides unique things to us. What? Close to the earth, if we see, this distance is just 1 astronomical unit. It means from the sun light can reach to earth within 8 minutes, almost 8 minutes. If we see other star system which is much away from the earth, and this is called Alpha Centauri triple star system, and the light from this star can reach to earth in almost 4.2 light years. So light years is again a unit of distance. It means light has to travel almost 4 years to reach to earth, and while from the sun it takes only 8 minutes. So this is the closest thing this star is providing us, and we can have several instruments to observe great details of the sun. As I progress in the following slide, I will show what we have understood about the sun, and then I will connect that information has helped us to understand aurora in a very different way than the ancient civilization which could not understand the aurora, and they connected it with different other stories and myths. Just to understand, We all know that sun sends lights in different wavelength, means different color. But the visual light from violet to red covers a large portion. The y-axis in this plot is irradiance, means flux. So most of the light, almost 50% light, if we say from the sun, is coming into visual light, to which our eyes are sensitive, and that's why we really appreciate the sun so much. However, some lights may be less than 5% in ultraviolet, and we can see the remaining portions are in other wavelengths like infrared and other higher wavelengths. So it means in using the concept of physics, it's possible. I will not go into detail how do we calculate, but there are ways if we have understanding which color of light is in what fraction. If we can know this from any source, we can know the temperature of the source, something like black body temperature. And now using this concept only, we know that the temperature of the sun is around 5000 Kelvin. The yellow lines, if you say yellow area covered, is like from the space observation, and we can see that from the ground there are some dips. It means our atmosphere and different gases absorb some radiation and don't allow us to reach on the earth, but still enough light reaches to us. And for a long time we were not understood actually how does sun create this much light. Only after the discovery of nuclear fusion, development in nuclear physics, scientists could appreciate that in the sun also this process may be happening, and this is now actually established by further observations of neutrino and other things. We now know that in the sun 4 hydrogen atoms actually fuse together to make one helium atom, but in this process there is a mass loss of around 0.7%. It means if you compare the mass of this 4 hydrogen and compare the mass of 4 helium, it's not equal. There is some mismatch in the mass, and that 0.7% less mass of the helium is converted into the energy by this equation E equal to mc square, famous Einstein equation. And that mass conversion into energy actually is in the gamma ray, if we can see here, and that gamma ray propagates out and converted into other wavelengths which we observe from the sun. So if we just understand, it means that inside the sun mass is being converted into the energy. And if we just calculate by the solar luminosity how much mass is being lost in the sun in the nuclear fusion, we can see here that there are 4 million tons per second mass is being lost. It appears very huge. But even if we calculate the total lifetime of the sun, almost billions years, and we calculate this is only a small fraction of the sun current mass. So we can understand sun has a huge mass. And even if this huge mass is like converting into energy per second, the sun may survive next several billions years. Of course, the stellar evolution don't go linear, and there are different processes at different stage, and that can take sun into different branch of nuclear stellar journey. Sun is very close, as I mentioned. So physicists have understood the sun in quite detail, and now we know that inside the sun, here at the core, nuclear fusion happens, energy propagates out into the form of radiation, then into the form of convection, like we have a water boiling and there is a convection current in that. So then up to some region the energy propagates into the form of convection, then it's from the photosphere, this is the layer, and outer layer is called corona. The outermost layer of the sun is called solar corona. So we have great understanding of different layer, but what we now understand that in the sun the temperature inside is not constant. If we can see here, first the temperature is decreasing outside the photosphere, and then if we can see here slightly it's increasing, and in here there is a very sharp increase. Even physicists are struggling to understand why temperature in the transition region and corona is so huge, because the general principle of physics suggests if we go away from the source, like here the source is solar core where the energy is being generated, if we go out the temperature should drop, but much away from the sun in the higher atmosphere temperature suddenly rises. And there are different theories and has been developed to understand this process and problem, coronal heating problem, but still we have not reached to a very conclusive picture. So as I mentioned, different layers of the sun have different temperature. It means if we have instrument observing sun in different wavelength, because each layer have different temperature, that will correspond to dominant one wavelength coming from that region, we can see different layer of the sun. In the photosphere you can see here there are different spots. So when we see sun in a white light, this image is taken from SDO AIA NASA mission. We can see that there are different spots on the sun, and these spots are black, and then it means they are cooler in compared to other region, and some spots are much bigger, and also you can notice that the spots on the top are moving slow than the spots near the central equator. It means sun does not rotate with one constant speed. Different latitude of the sun rotates with different speed, and that has a huge impact actually in generating the magnetic field inside the sun. Differential rotation and then convection I described before, both together can amplify the magnetic field. These dark spots were observed for a long time, even starting from 17th century after Galileo. There are extensive like development of telescope and then continuous observation. Only this scientist helped us to understand that these sunspots are not only cooler region because they appear dark, so one can easily understand they are cooler, but they are highly magnetized region on the sun. And this scientist used the concept of Zeeman effect. So physicists, many students can appreciate that Zeeman effect is a very important theory and experiment which can measure the magnetic field of the light coming, and if it encounters some magnetic field, there will be splitting in the spectral lines. So using this concept, Hanle measured the magnetic field in the sunspot, and if we zoom one sunspot, we can see that the magnetic field in the sunspot is going around 2000 to 4000 Gauss. Just to compare, Earth's magnetic field is close to less than 1 Gauss, 0.5 Gauss. It means it's thousands or 2000 times bigger and stronger magnetic field in one sunspot. So we appreciate that these sunspots are very highly magnetic field region, and their temperature, if we compare with the normal temperature region here, it's quite less. This has it means inside, so for a long time there was no proper understanding how this magnetic field are generated on the sun, which is coming on the photosphere. There are like a group of people working in this field, solar dynamo, that try to explain how the magnetic field inside the sun is being created, and that theory is called solar dynamo theory. That basically deals with convection, differential motion, which actually can amplify the magnetic field and convert from poloidal to toroidal. And if you see here, this model is able to explain the number of sunspots rising and coming down. It means on the face of the sun at a time, the total number of sunspots are not constant. They are increasing, decreasing, and again becoming maximum. So this pattern is called solar cycle. When we have more number of sunspots, something like this, if we see here, with time, with each 11 years, the number of sunspots plotted on the y-axis are higher, and then coming down like descending phase, then again ascending, then again reaching to maximum. This pattern of sunspots becoming maximum repeats each 11 years, and this phenomena is called sunspot cycle or solar cycle. As I explained that we all know that magnetic monopole does not exist. So most of the sunspots, if we see, are bipolar in nature, and this different color blue and red shows the negative and positive polarity. So these are the storage of photosphere, how it appears, the disk which we see. Then we have another layer of the sun called solar chromosphere, and we can see that these are lot of dynamic events are happening. So sun appears static, not changing, but if we have good instrument, we can see that lot of plasma and magnetic field variation, reconfiguration is happening with time. And this clearly suggests that physical processes are happening at different scale, and one need to understand in a great detail to understand what is happening inside the sun. Then the outermost atmosphere of the sun can be observed in UV and X-ray, and we can see that the regions where there were more sunspots, if you remember, like notice the same location where there were sunspots, intense brightenings are there. It means there some processes are happening which is like bringing lot of energy from lower atmosphere of the sun. So from photosphere, chromosphere, energy is coming up into the higher atmosphere corona. I am just trying to bring first lot of facts because these are the phenomena happening on the sun. To understand anything happening on the earth, we need to combine all these phenomena to understand what is the impact at the earth. So solar flares are one explosive events we can see here, which is localized sudden brightness enhancement in different wavelengths, especially in UV and X-ray. So we can say here that solar flare means intense brightening, and sometimes these are associated with huge mass expulsions from the sun, something like this. In this movie, you can see here, lot of mass is coming from the sun. It's like billions of tons of mass actually. And these events on the sun happens very frequently. If the sunspots number are large, this event can happen 3, 4 in one day. And if the sunspots number on the sun are low, these events happen 2 to 3 in a week. So still it is very frequent and but episodic event. So sun also loses mass not by nuclear fusion which is happening in the core, but also by the coronal mass ejections. If, and we all know that Earth is orbiting around the sun, if this CME's coronal mass ejections are in a direction reaching to the Earth, it can damage. But most of the time, since Earth is orbiting and this CME may happen in all directions, it may not reach to the Earth. And there is one discipline trying to understand something observing on the sun like huge mass ejections, and then trying to understand whether it is reaching to Earth and what time it is reaching. This branch is called like CME prediction like group. In different space agency have this focused group working, looking continuously at the sun and trying to understand when such CMEs are going to reach. Sun also loses mass by solar wind. So we have nuclear fusion by which sun is losing mass, then we have CME, coronal mass ejection, and then we have solar wind, which is continuous stream of particles coming from the sun. So the difference between CME and solar wind is CMEs are episodic event which happens at times and stops sometimes, then again it happens. But solar wind is continuously charged particles are coming from the sun. This is again a huge process by which sun is losing the mass. And as I described, like scientists try to explain all the phenomena. For that, first they classify the events into different categories. So solar flares can be classified into different categories. If it is very less intense, it can be A. If it is most intense, it can be X. So these different peaks are basically representing most intense flares. So I will not go into detail of that, but these CMEs and solar wind coming from the sun actually affects the whole space weather. Space weather means like on the ground we have terrestrial weather and we are very concerned whether it will rain, light, humid and other things. In the same way, in the space, scientists are concerned whether at a time, at a place, like suppose any place in the space, what is the level of plasma, how dense the plasma is, what is the magnetic field at that point, what is the electric field, because these plasma parameters in space can affect space infrastructure. Suppose you have a satellite orbiting, and its path has been made in a way that it can go into this much dense region. Suddenly, huge mass comes and density increases in the path of a satellite. Satellite may experience enough drag and it can deorbit. Something like that. Not only that, satellites are affected. When these masses reach to the Earth, they can actually affect communication, human space exploration, in fact, aviation. If you go and search, you will find that many flights paths are diverted, are rerouted when such big storm happens. So even the airlines are trying to take help of these understanding from the solar phases to understand how they need to reroute their commercial or this aeroplanes. Electric power grid, and these when they reach to the Earth, you can see here a lot of particles when they hit to the Earth's magnetic field. You can see from the day side to the night side there is again a process called magnetic reconnection. And this allows the particles to go inside the Earth into the polar region. You can see here the most of the intense aurora is actually in the polar region. This region is called auroral oval. It means where mainly aurora forms. In the coming slide I will show it forms only in the polar region, but still some people can see from the lower latitude and there is a specific region for that. But this phenomena is actually happening into the Earth's polar region. So I will not go much into detail, but there are different space weather. Like they can lead to radio blackouts that can affect airline communication and high frequency radio operations. But then intense radiation can come at the time of solar flare and they can again have different impact, like they can ionize the top atmosphere and that again can cause atmospheric drag to low orbiting satellites. Then we have geomagnetic storms. The whole Earth's magnetic field can be perturbed for several hours and it takes long time to recover. And this different category of events, if we club all together, we can see that sun can affect everything, probably all the space and ground technological system. And that's why it's quite important to understand what is the role of sun in governing these like perturbations. Recently, you might have read probably in the news that SpaceX, which is a company which has several like Starlink satellites to provide internet in different countries, the 40 of the satellites were actually damaged once in the year, you can see very recently in 2022. So these impact from the sun, CME and all have a huge things, and they can damage lot of infrastructure. And that's why scientists actually basically in IIA and other groups are trying to understand sun earth connection in a very scientific way. And that includes understanding what is happening on the sun from deep inside to the outside in the solar corona. If something happens, what are the physical processes? Why not always CME happens? Why not always solar flare is happening? So to understand the complexity of the process involves a lot of theoretical modeling and observations. Then if something happens on the sun, is it easy to know when it reaches to earth? This whole discipline, there are separate sub-discipline dealing only with the propagation, because we need to do like division of labor, division of work, and then different scientists are working in different sub-discipline to understand the detail of the process, and these are very challenging ones. So I will not go into detail, but we can see that even a CME, if it happens on the sun, it's coming, its speed is not constant as it's moving away from the sun. We can see some CME may have high speed, then later low speed. Some CME may start with low speed, come with high speed. So each individual events have very different kinematics as they travel out into the interplanetary medium. And that's why it is very challenging, because the medium between the sun and earth is again filled with lot of plasma and other magnetic field perturbations. So when something comes from the sun, it's not easy to take its speed or direction trajectory and simply extrapolate it. It's quite challenging. So people trying to deal with this take help of observation, do theoretical modeling, and deal with lot of hydrodynamic, magneto-hydrodynamic equations. So in nutshell, just to summarize, geomagnetic storms are the perturbation in the Earth's magnetic field, geofield, and then substorms happens the phenomena night side of the Earth, and these two geomagnetic storm and substorm sometimes together, sometimes alone can also lead to the aurora. So I will go into detail in some time. So basically, if we see, I explained that aurora mainly happens in the polar region. So when the charged particles reach to the Earth, they are actually guided by the Earth's magnetic field in the polar region, and we can see that a lot of particles are entering into the Earth's polar field, polar region. And when they reach, they actually interact with the Earth's atmosphere, and then collisional excitation happens. And again, we know that how light is produced. The excited atoms come to ground state and emit light. Depending on the different species into the atmosphere, different types of light will be emitted. So these are the region, and we don't always observe, because like event coming from the sun should be strong enough to put lot of particles into the polar region. Then only this phenomena will be enough intense to see in the auroral region. And we can see that people from the ground can observe something like this, but not everyone can observe. Level of solar activity, not always. Intense solar activities are associated with such aurora. So it means that aurora we last observed is connected to the something big activity happening on the sun. Then proximity to the auroral oval. I explained that auroral ovals is only in the polar region. But if we are close to the auroral oval, high latitude, we can better see and have frequent chances to see aurora. But local weather and time, we cannot see in the day, because daylight is much stronger and these auroras are faint, we cannot actually see them. And of course, the intensity can also be governed by the seasons, spring and fall, because the geomagnetic fields are well aligned to take a lot of particles from the solar wind. So just to summarize in nutshell what's happening, solar origin particles colliding with the atmospheric particle, and they actually excite, and again de-excitation happens, and these beautiful colors can be seen. So this is the, depending on the which atoms are excited, like if oxygen is excited, we can see red and green. If molecular nitrogen is excited, that will give probably blue and purple light. So depending on the species, we have different colors in the aurora, and sometimes combination of color will give like different appearance of So we can see in the previous video animation that aurora has different shape. So why different shape happens? Scientifically, it is very difficult actually to reproduce such shape, but general understanding is that it matters from where the electrons come into the magnetosphere and where do they precipitate, how do they precipitate, and the viewer's position also, like from which place you are seeing. The same aurora from different place may have different appearance. So still there are research going on in this direction. But just coming to the old pathology, is this aurora happening new? In the beginning, I told sun is there for billions of years. Aurora is happening all the time, and that's why even if you go oldest civilization, they all have mentioned aurora in some or other way. So here there is one painting in 1591, and we can see here that in this painting they are trying to people are trying to suggest something into the space. So this suggests that people have observed aurora, and in fact, you can see in different culture they have associated with either with prophet, god, deities or something. So this is the story around the aurora. There is again another painting, and we can see here that here in this Norway, again a polar country, there the appearance of aurora has been associated with dead women. So something, it means aurora has always been either fear, amusement, surprise or something. So not very accurate understanding was there. In fact, in Norway, people believe for a long time that when they see aurora and wave a cloths on them, the intensity increases. It's again a coincidence. So just I am putting these pictures to suggest that there are enough paintings available from different like 1500, 1600, even 10th, like 11th, 12th centuries also. So I will not go much into detail, but this is a beautiful painting. Again, one aurora happened in 1865, and we can see that people have tried to sketch it. So it has always been beautiful, but the scientific understanding of aurora started much late. We can see here that in 6th century BC, people started putting in scientific thoughts, not using with some like fear or surprise. People thought, Xenophon thought, the Greek philosopher, looked at several aurora actually in his lifetime and tried to thought that these are moving accumulation of burning clouds. He thought that clouds by some phenomena are burning and we see different colors. Not very accurate. But Galileo Galilei, he also thought. So he is one of the like early astrophysicists. But we see how this I want to show to for the young children here that any discipline does not start suddenly. Of course, there is sometimes jump into the field, but it grows very slowly. You can see here that series of physicists. In fact, the Rene Descartes, the last line, was a very famous philosopher, astrophysicist, mathematician. In fact, he also thought that these auroras are caused by the reflection from ice crystal at high latitudes. Because in high latitude there are enough crystals, ice, and he thought that sunlight is reflecting from there, and what we see is that beautiful colors. Galileo Galilei thought that air from the Earth's surface is rising above, and that air is illuminated by sunlight, and then we see aurora. So these are just like emerging scientific thoughts at that time. But then observations help. People observed sunspots for a long time, right? And in fact, there was a time when on the sun there was no sunspots, almost minimal sunspots. That time is called Maunder minimum. That coincides with the time 1645 to 1700. Something like 65 years on the sun, there was no sunspots. There were no sunspots, and then at that time, people even living in the northern countries could not see aurora. So for the first time, from the experience, they understood that something sunspots may be connected to this aurora. So see how the discipline develops. And then we after the telescope, like advent of telescope, we have again observations. And if you see here, the number of days with observed northern lights very well have some association with sunspots. Again, with hundreds of years of sunspot observations continuously and counting the aurora day from the northern countries could help some of the scientists to understand there is a connection between sun and aurora. But the physical process was still not very understood. So this is a scientist actually, Christian Birkeland. He made a very significant contribution to auroral physics. And what he did an experiment called Tirela experiment. But his experiment is not like in isolation. Just the discovery of electrons happened in 1907, the atomic model. And then he used these concepts, and just see few years later, he proposed a theory. In fact, he made a dipole like a magnetic field, put into the Earth like model inside, and since the electrons were already discovered, he put the series of electrons to these magnetic regions, and he could produce aurora in the lab. This is the setup he used. So it means he could see beautiful lights into the lab. And then this experiment had a lot of like challenges at that time, because we can see technology and any things were not available at that time. But from this experiment, he could conclude that some electrons are coming from the sun, and probably that are leading to aurora when they reach to the Earth's magnetic field. This is one of the closest theory. Even today we have similar but little different and advanced theory, but this is the starting point of the current discipline of auroral physics. Then after that, a big storm on the sun happened in 1859. This event is called actually Carrington event. So there was a Carrington, again a solar astronomer, looking at the sun, and he found sudden brightening on the sun. And after 18 hours, probably within a day, on the Earth there was a huge perturbation. This magnetic field measurement is taken from the London Observatory, Kew Observatory, London. Here we can see that a huge decrease in the Earth's magnetic field. And that Carrington made this sketch, the location where he could see the brightening at that time. In fact, Indian Observatory in the Bombay also observed this huge depression in the Earth's magnetic field. We can see the Earth's horizontal component of magnetic field of few thousands, 10 to the power 4 order, suddenly decreased by few hundred nanotesla. And this decrease was associated with a lot of auroral activity. If you see this map, people in different region could see the aurora at the same time. So it means people established in 1859 itself thought that when a big perturbation in the Earth's magnetic field is happening, at the same time aurora can also be seen, and that they connected with the sun. So there is now much better connection between the sun and Earth in terms of aurora and geomagnetic perturbation. If we can see that the discipline had now much more clarity, and when a big storm happened in 1921, the New York Times clearly credited that sunspot in the region for this big geomagnetic storm and also the northern lights. So we can see almost 100 years before we have clarity about these processes. But still we have not observed something coming from the sun. Just I want to make this emphasis. See, lot of development happens in some field where we don't observe but we infer. In fact, this scientist in 1958 suggested that charged particles must be coming from the sun because sun outer corona is so hot. I explained in the beginning, corona is million-degree temperature. He made a theory, suggested that solar wind must be coming, but we did not have observations. The first observations of something coming from the sun happened only in 1959. So see how we are developing. We developed a lot of theories, but there were no observations. The first observation, Soviet spacecraft Luna actually observed something coming from the sun, the particles, because we need to go into space. On ground, these particles don't reach. And then the CMEs, which I showed the videos in the beginning, that are actually taken from the recent instruments and recent missions, NASA missions. But the first NASA mission actually went into space 1971, and that actually images CME, coronal mass ejection. It means the whole development of auroral physics happened, connections were developed, but the clear observation that something coming from the sun happened much later. And now we have, with time, we see better understanding that Earth's magnetic field perturbation, geomagnetic storm, and the solar cycle, sunspot numbers are very well correlated. In fact, from the Finland, this data is there that the number of nights we see of aurora is very well correlated with the geomagnetic activity, the perturbation in the Earth's magnetic field. And since in the polar region there would be long, several months like daylight, several months night, so we actually see the white bands where there are no data. So just to summarize, these events, aurora is happening with the big perturbation in Earth's magnetic field, something coming from the sun, big CME. Now we want to understand how this event happened. Because this event is observed from Ladakh, we can see clear aurora in the northern region, red aurora. We did not see any other color. I will explain this why. Yeah, we can see. In fact, we started doing some analysis and we found that this is we see on 11th May, on y-axis you assume that Earth's magnetic field perturbation. So from the base value, it's decreasing. Earth's magnetic field has a huge perturbation on close to 11th May, and then it takes several days to recover to its own like ground like base value. So this huge perturbation, as I told, the last data of several decades have suggested that geomagnetic perturbation is responsible for aurora, but not always. There are other physics, like I told, substorms are there in the night side that can also lead to the aurora most of the time. But here, these events, the aurora of object from Hanle and all across the globe, is due to this perturbation in the Earth's magnetic field, which happened on 11th May. In fact, this is the picture taken from Hanle. We can see again the red aurora. And this event is observed from different countries. We can see that as we increase the latitude, we may see other colors. Then higher latitudes, as we go to the more polar region, different colors. Germany, UK, Russia, and even from the southern hemisphere, we can see Chile, New Zealand, the aurora has been observed. As we come to lower latitude, we see more reddish color. People observing from more northern hemisphere, more north, close to polar regions, they observed much different color. We started doing some analysis of this event. In fact, there are reports that these events of May 24 have damaged several things, like Transpower New Zealand Limited declared grid emergency, power grid emergency. Telecommunications companies in the US were prepared to respond to disruptions. Aerial drones actually lost controls. In fact, there is satellite GOES 16 which continuously monitor the GOES X-ray flux coming from the sun. It also like stopped transmitting all the data for 2 hours and then it was restored after some time. In fact, Starlink satellite experienced degraded service, but of course did not damage. So the point is, this storm had huge impact. Just to compare in the history, how big was this storm? If we compare last few decades, such a storm happened only 20 years before in October, November 2003. We can see the Earth's magnetic field has a huge decrease. And before that, if we go, only in March 1989. So this strong event happens. We are trying to understand how frequent are they and what are the processes that decides when it will happen. Just to compare these other two strong events into the context of this event, we can compare. So let us compare October-November event. We can see that the decrease in the Earth's magnetic field is something like more than 400. If we compare with the previous, it is almost again close to the same value, 400. So this is as strong as something happened in 2003. And this is slightly stronger. And if you see the performance, even at that time, this event was associated with huge aurora all across. And this event was again very strong. It damaged many satellites into space. Some satellites fell temporarily, and some like transformer and other things on the ground were damaged, especially in the polar country. And now we understand as we go in time like ahead, this was 20 years before, more and more dependence to technology is coming. Even 1 hour, 5 hour power grid damage, the whole city may be disrupted, lot of services will be unavailable. So this shows that we need to be aware and understand what is happening on the sun. And then to compare March 1989 event, this was a very huge impact, very huge intense storm, geomagnetic perturbation, and we can see it is much stronger than 400. It is going to 600 nanotesla down the DST index, the magnetic field perturbation. And this led to huge power blackout into the Canada. Almost for 9 hours there was no electricity. So in this Quebec city. So we can see that these strong storms reaching to the earth, of course they create beautiful aurora, but they are very dangerous. So we can say beautiful and dangerous. And that event also had auroral sites, like 1989 event. So now there is a very firm connection. Something big happens on the sun, very great plasma ejections coming out, reaching to the earth, leading to perturbation in the Earth's magnetic field, and then auroral sites from different places. But the aurora from the Hanle, I explained that at different altitudes, since there are different concentration of atmospheric species, different lights are produced. Like in the top level, we can have oxygen, atomic oxygen that can produce red light. If the particles are strong enough, they can penetrate much deeper down into the atmosphere. They can again excite atomic oxygen and that can create blue, green light. So red, green. If they come much deeper, they can create blue light. due to the excitation of ionized molecular nitrogen. And you can see here the both red and green lights are by the atomic oxygen, because the lifetime, the density of the oxygen at these two altitudes are different. Like here above 200 kilometer, here close to like 150 are at that height. So depending on the density of the atomic oxygen, that will decide whether the de-excitation happens only by the transition, free transition, or they can collide with other particles and de-excite themselves. So these are the different physics, but recently we try to understand why aurora from Hanle is only red. And we can see that we are not actually up, since we are at here, low latitude, let us assume we are at O, this point. So we are not observing aurora at the lower height. Basically, we are observing aurora at higher height, to put it simple. So basically, we are not observing aurora overhead, but we are observing much higher. As I told that this aurora happens under very upper altitude, red, then green, and lower latitudes are blue. So we can see that we are observing much higher, because the Earth's curvature would not allow to see lower altitudes from the low latitude. So basically, as in the previous pictures you also saw, most of the aurora we see from the low latitude is basically red. And auroras are observed also on other planets. The planets which have a strong magnetic field, like Jupiter, we see very intense aurora. The magnetic field of the Jupiter is 20,000 times stronger than the Earth. And aurora has also been seen from the international space stations. We can see here this beautiful video they have recorded. So the point is, Sun and Earth are very well connected, and the objective of this whole discipline is not to just understand one star and one planet. As I explained in the beginning, the general objective is we understand one star and one planetary system very well, because they are very close to us. Use the same process, because the physics is the same happening in different stars. They are made of plasma, similar to the sun they are. So use this knowledge to understand much vast and bigger cosmos which are much away. This is the whole bigger objective of this whole understanding of sun earth connection. So with this I thank you, and this video shows that something coming from the sun. Actually now we have the facilities to observe such mass ejection continuously from the sun to the earth, and we can see when it is reaching to the earth. Whether this arrival time of big eruptions from the sun exactly matching with the aurora time or geomagnetic perturbation, it's not exactly matching. There are some physical process, because these structures are so big, and it is still not understood whether the leading portion of this big mass ejections will directly impact the Earth's magnetic field or the trailing portion. So there are much physics to this to understand the whole complex interaction between sun or the solar material coming from the sun, CME, and the Earth's magnetic field perturbation happening due to this. So I stop here. Thank you.
Thanks a lot, Dr. Avish. I hope all of you enjoyed that talk. I think it was quite informative. Now we'll open up the stage for some questions and answers. Can I ask my volunteers, Shivani and Kamal, to take the mics around. Let's just wait for the mic so that people on YouTube can also hear your questions. We have one question in the back there.
Thanks for the nice talk. In the initial slide, you showed about variation of the luminosity.
Sorry, one second. I don't think the mic's on. We'll just go to the other mic.
I think now it's on.
Yes, thank you. Go ahead.
So the initial slides you showed about the luminosity variation of the stars. In that you also showed the sun's luminosity variation, and I saw that at the recent times, meaning last few years, the luminosity is actually more fluctuating compared to previous time. Is the case, and why it is happening?
Yeah, so actually that plot have different years. So when the solar activity is on rise, means high solar activity, that time we expect much more variability in the flux from the sun. So basically in the sun, if you see the 2012 and 13, that coincides with the solar maxima. We have huge variations.
But that seems to be continuous, right? Over the years.
Yeah, because maxima will stay for some time. So yeah, that few years it has a huge perturbation. So let me go to that slide. Yeah, so sorry, it is taking some time. Okay, just wait. So you can see that here little more fluctuations are there because these are the periods coinciding with solar maxima of last solar cycle 24, right? So we can see this is the maxima, solar activity were at high, lot of sunspots are there on the sun. While for the star we don't know the cycle of that star, but although solar type, but point is it has larger fluctuation variability than the sun.
Next question from the audience here.
Hello sir, this is Shashank. So I have a couple of questions. So the corona mass ejections that you spoke about, what material is that usually? Like, and does it really get into the Earth's atmosphere and reach the Earth's surface also, or does it kind of get burnt while it reaches there? And then the second question I had was on how much time those ejections take, so that can we predict, say, suppose I want to go to Norway, so and I am looking at these ejections are happening in month of say March, then I should plan to go there in June or July this year or next year. Is there any formula that we can use to calculate that?
Yeah, so good question. So the first one, what are the materials? Actually, this is the coronal material and some chromospheric material. So basically 90% hydrogen. In terms of number density, if we talk, CME has 90% hydrogen, and then ionized hydrogen, and of course helium. And these are huge mass. Other elements are also there, but in lesser like fraction. About the timing, of course, we have satellites looking at the sun, so we know when big CME has happened. But it's quite not very well understood when they will reach. Just for an example, I have showed this plot. Suppose we observe CME happening here at this time. Although we have a facility to observe continuously, but there is no point if we track a CME to longer distance because already the CME is about to reach. So if we try to know at what speed this is moving much up to the delay, the prediction forecast like time, advanced time will be much less. If we just look closer to the sun and try to understand when they will reach, their speed can vary, their direction can vary, there are different physics happening. Since CMEs are happening in the sequence from the sun, the faster CME from the behind can catch the preceding CME, momentum exchange can happen. As I told, they are traveling into a denser medium, plasma medium, solar wind is always flowing from the sun. So it's like a big ball you are putting in a flowing river. And the speed of river is not very well understood, the perturbation in the river is not understood. So it's like a hydrodynamic problem. And people dealing with this are doing that MHD forecast, MHD model forecast. They took the ambient medium condition, they try to put CME bubble into that medium and then try to solve how it interacts with the medium. So it's quite challenging, but of course, with the advancement in last couple of decades and especially last decade, have made good understanding of the prediction ability. But still the arrival time prediction at the Earth is not very accurate. The error can be more than 12 hours or 20 hours. On average, it's 12 hours.
Okay. So coming back to the material part, so mostly gases, like they are like because of the temperature, they are kind of solidified gases. But there are no rocks or stones or those type of materials coming out of the sun.
So it's simple plasma. Sun is made up of plasma. So outer atmosphere is corona, very high temperature. So if you use simple equation, you can know that this is highly ionized material. So it is just plasma coming, but physical processes are in such a way that it stores lot of plasma into certain magnetic field region, and then there are again some processes by which this whole equilibrium is disturbed and the whole mass is ejected. It's like you can assume very like crude example, you can have a spring, put lot of weight on that, it can be compressed and compressed, store lot of energy, but then you perturb the spring by some process and the whole mass put on the skin can be ejected out. So this is something like that rubber spring putting lot of mass out. But this process is called magnetic reconnection, in which reconfiguration of magnetic field is involved to lead such type of big material coming out.
Now, last thing, you showed one slide where one of the scientists was doing an experiment for recreating the aurora.
Yeah. So yeah, that experiment is, you can see the milestone in auroral physics.
Right. So today, do we have active labs across the world created like this where people can go and experience who cannot go to maybe North Pole?
Yeah, this can be done now in different laboratories. So you can see this is a 100-year-old experiment. Now, in people doing plasma physics in laboratory have created such type of aurora into the lab. It can be done.
Do we have such labs in India somewhere?
Yeah, in India I'm not very aware. So this whole, but in IPR it could be there. In Gandhinagar there is a specific institute, Indian Institute of Plasma Research. So there, this facility must be there.
Thank you, sir.
We'll take one quick question from YouTube, which I think is also a valid concern, which is, if we could predict the occurrence of a solar storm, is it possible to change the trajectory of a satellite? What are your comments on that?
Yeah, so satellite trajectory cannot be changed, but few instruments can be put off for some time. So the minimal damage will happen. Yeah, so this is a very good question. Like something is coming from the sun, you cannot stop. It's like water coming from ocean, you cannot stop. But of course, if you know something is coming, you can safeguard yourself better. So in the sense of satellite, in fact, earlier it has been done that NASA has switched off some of the major payloads and to avoid damage directly hitting. Because if it is not on, it will not be that strong damage. So it can be like optimized. So the risk and damage can be like less, can be less, yeah.
Any other questions from the audience here? We have one question here. Can we get the mic here?
Hi sir, I'm Apurva, and really great talk, loved everything you talked about. You talked a bit about auroras and its history and how it led us to better understanding the sun. So, can studying auroras deeper help us understand the properties of the sun? Or why is it that we're trying to model auroras better?
Yeah, so this is a very good question. So we are trying to model aurora because the particles coming from the sun are not of the same energy. As I told, CMEs are happening and ambient medium particles are also there. So when this CME happens, they may sometimes drive a big shock ahead of it. And this shock can accelerate the particles of the ambient medium. So the particles can have energy of a broad range. It can have kilo electron volt, mega electron volt. So this we don't understand very well in terms of understanding how much energetic particles will be coming from the sun. And since the particles are not coming straight, they have a trajectory following the Parker spiral and ambient magnetic field. So if we understand at which location, what time aurora happens, at what altitude it is happening. Altitude means what type of energy of the particle which are penetrating. Higher the energy, deeper down they can penetrate into the atmosphere. So if we understand the auroral physics at what height it is happening, what type of particles they are, we can understand aurora in a better way. So not all particles are coming from the sun. Suppose some particles from the preceding CME has come. They have entered into the Earth's magnetosphere. In some current system like ring current or the plasma sheet into the night side magnetosphere, suppose they are there. A little perturbation like from here. Suppose a preceding CME can put lot of particles here into the plasma sheet and they can be put here and some disturbance like substar may happen. But then next CME may come and just disturb or put the disturbance in this equilibrium and put lot of particles. So directly these particles are solar origin but not from the immediate CME. So it's very difficult to model, that's why. And modeling will help us the processes happening like what CME is doing during the propagation, accelerating the particles and all. So that's like particle acceleration is a different discipline dealing with what type of particles are accelerated, where they are reaching to Earth or they are escaping by this particle trajectory. Yeah.
Okay, due to constraint of time, we'll pause the question and answer session here. Let's thank Vagish once again for this wonderful talk.